Chapter number 13, Electromagnetism. Electricity and magnetism are different facets of electromagnetism. A moving electric charge produces magnetic fields. Changing magnetic fields move electric charges. In previous chapter, chapter number 11, we discussed electrostatics, and in that chapter we studied that charges at rest produce electric field. But when charges move, so due to their motion, magnetic field is also generated. So a moving electric charge produces magnetic fields. Magnetic fields from electricity. A static distribution of charges produce an electric field, which we discussed in electrostatics. Charges in motion. An electrical current produce a magnetic field. Electric current is an example of charges or electrons in motion. So when charges are at rest, they produce electric field, but when charges move, they generate magnetic field. This current carrying wire in which electrons are in motion produce magnetic field around it. For finding the direction of magnetic field, we can use right hand, and according to the right hand rule, our thumb indicates the direction of electric current flowing through this wire, and if we place our thumb in the direction of electric current flowing through this wire, then the fingers shows the direction of magnetic field. When we curl the fingers around this current carrying wire, the direction of field is represented by fingers. When the wire is in the plane of the paper or screen, the field is perpendicular to the paper or screen. Note the symbols used for the field pointing inward, like the tail of an arrow, and the field pointing outward like the tip of an arrow. A long and straight wire creates field with magnetic field lines forming circular loops. Magnetic fields from electricity. A wire carrying an electrical current causes a nearby compass to deflect. Here we have a current carrying conductor or wire, and we have placed a magnetic compass near to this current carrying wire. Because electrons are in motion in this wire, so there is magnetic field around this wire. When we place this magnetic compass near to this wire, that is current carrying wire, the compass showed deflection, and this deflection of compass tells us that there is magnetic field around this current carrying wire. The compass needle near the wire experiences a force that aligns the needle tangent to a circle around the wire. Therefore, a current carrying wire produces circular loops of magnetic fields. Magnetic force on a current carrying conductor. Electric current is an ordered movement of charges. We know that when charges move, we get electricity or electric current. A current carrying wire in a magnetic field must therefore experience a force due to the field. Here we have a current carrying conductor, and there is magnetic field around it, and when we place this conductor, that is current carrying conductor, in a uniform magnetic field pointing inward to the screen or paper, the magnetic field of this current carrying conductor and the uniform magnetic field in which this conductor is placed interact with each other. Due to this, a force is applied on this conductor. The force depends on the current I in the wire or conductor and the length L of the conductor that lies in the field. So F is directly proportional to I into L. I is current flowing through this conductor and L is length of conductor. F is force experienced by this conductor or wire. So F is equals to BIL. Here B is strength of the uniform field or magnetic induction. If a wire is placed in the field B at some angle theta with it, then the force is F is equals to BIL sine theta. We can write it in vector form as F is equals to I into L cross B. Here we have taken the cross product of length and magnetic field induction. So the length and magnetic induction both are vectors and they are showing the cross product here because sine theta is replaced by this cross product. This force F experienced by this current carrying conductor depends upon current flowing through the conductor, length of the conductor, and magnetic induction or magnetic field strength and the angle between L and B. By keeping BIL constant, we can get the maximum or minimum force by just changing the angle theta. If the theta is 0, then we get minimum force. If the theta is 90 degree, then we get maximum force. As we know that force is a vector quantity, so we can find its direction by using Fleming's left hand rule. The thumb and first two fingers are set at right angle to each other, with the first finger pointing in the direction of field, magnetic field, and second finger pointing in the direction of current. The thumb gives the direction of force. For finding the unit of magnetic induction, we can rearrange this formula and we get B is equals to F divided by IL. SI unit of B magnetic induction is Tesla, and 1 Tesla is equals to 1 Newton per ampere per meter. Newton is unit of force, ampere is unit of current, and meter is unit of length. So from this formula we can say that if the force experienced by 1 meter of a wire carrying 1 ampere current placed perpendicularly in the magnetic field is 1 Newton, then the magnetic induction is 1 Tesla. We can use another unit for magnetic induction, that is Gauss. 1 Gauss is equals to exponent minus 4 Tesla, and 1 Tesla is equals to exponent 4 Gauss. Magnetic flux is represented by phi, a measure of the number of magnetic field lines that cross a given area are known as magnetic flux. Here we have a plane and magnetic field lines are passing through this plane. Only those number of field lines which are passing through this plane are known as magnetic flux. Magnetic flux is defined as the scalar product between the magnetic flux density B and the vector of the surface area, vector area A. So phi is equals to B dot A, and we get phi is equals to BA cos theta. Here phi is magnetic flux, theta is angle between B and A, and B is magnetic flux density, A is area of the plane. Phi is a scalar quantity. Its unit is Tesla into meter square or Webers. In this figure, plane is parallel to the B. Magnetic flux density and vector area of this plane is perpendicular to the B. So the angle between A and B is 90 degree. So theta is equals to 90 degree. Putting theta is equals to 90 degree, we get phi is equals to BA. So we get maximum flux, maximum magnetic flux when the vector area and magnetic field lines are perpendicular to each other. One thing you know that direction of vector area A is always perpendicular to the surface of area. So we have this surface area of this plane. So its vector area is always perpendicular to the surface or normal to the surface. So if we have a plane and it is perpendicular to the direction of B, but its vector area A is parallel to the direction of B. So the angle between B and A is 0 degree because A and B are parallel to each other. Putting cos 0, we get phi is equals to 0. So we get minimum flux when vector area and B are parallel to each other. Magnetic flux when the angle between B, magnetic induction, and vector area A is 90 degree, we get minimum flux phi is equals to 0. When the angle between B, magnetic induction, and vector area A is theta is equals to 45 degree, then we get phi B, that is magnetic flux, is equals to BA cos 45 degree. When the angle between B, magnetic induction, and the vector area is 0 degree, theta is equals to 0 degree, then we get maximum flux phi B, magnetic flux, is equals to BA. Magnetic flux density. From the formula phi flux is equals to BA, which we discussed in previous slide, we can write B is equals to phi divided by A, where B is magnetic induction and that is also known as magnetic flux density because magnetic flux is divided by area. So here magnetic induction B is defined as magnetic flux per unit area and it is known as magnetic flux density. Its unit is Webers per meter square. Magnetic flux lines are continuous and closed. Direction is that of the B vector at any point. Flux lines are not in direction of force but perpendicular. When area A is perpendicular to flux, we get B is equals to phi divided by A. Magnetic flux density. You may be confused that I'm using different words for B. So what are other words for magnetic flux density? Magnetic induction, magnetic intensity, magnetic field strength, magnetic force or field intensity. All these words represent B.